Okay, in this presentation we're going to look at the negative binomial distribution. Now we'll come across the details of it shortly, but if you're familiar with the binomial distribution and the geometric distribution and Bernoulli trials, it sort of fits into that sort of bracket, that sort of category. And also, like the geometric distribution, there are two different ways of formulating a negative binomial. So there's essentially a type 1 and a type 2. So we'll come to that shortly. So, suppose that in a group of insurance policies which are independent as regards occurrence of claims, 20% of the policies have incurred claims during the past year. So that's the probability of a success. P equals 0.2. Okay, and it's a Bernoulli trial. Yes or no outcome for a particular trial. An auditor is examining the policies in the group one by one in random order until two policies with claims are found. Okay. Determine the probability that exactly 5 policies have to be examined before 2 claims are found. Okay. So this is what sets up the negative binomial distribution. How many Bernoulli trials must occur before you get a certain number of outcomes? That's one way of specifying it. Okay, there's two different ways of specifying it, which we'll come to them shortly. But essentially, exactly 5 policies. Okay, so there's going to be 5 trials, and essentially, what's the probability that 2 of them will be successes? Okay. So, the second question is find the expected number of policies that have to be examined until 2 policies with claims are found. Okay, so if you on average, how many do you have to search before you get 2? Suppose that there is a sequence of independent trials, and thus each trial has 2 independent outcomes, success and failures. In each trial, the probability of success and failure is denoted P and 1 minus P respectively. Okay, so that's just essentially a Bernoulli trial. I pretty much talked about that earlier already. Now, so there's 2 distributions. There's the type 1 and type 2. So they're similar enough, but there's a subtle difference between the two. This approach models the number of failures in a sequence. Okay, that's the key thing there, denoted K. In a sequence of independent and identically distributed Bernoulli trials before a specified number of successes, denoted R, is found. Okay? Does that sound like our question? Yes, no, we'll just wait until we see the second one. Okay? Then the number of failures, as we've seen, X will have a negative binomial or Pascal distribution. Okay, so essentially what we're looking at is the number of failures before you get a certain amount of successes. Now that seems like what we're looking for, okay? But it actually, we can actually use this one actually, just like rather than just slightly rephrase the question. Determine the probability of exactly 5 policies have to be examined before 2 policies with claims are found. So that could actually be 3 failures. Okay. So let's think about that one for a second. Now that's the probability mass function there for that. Okay. So yeah, that's it there. That's the key thing there. So R is the number of successes, P is the probability of success, F is the number, K is the number of failures, and this is the mean and the variance respectively. Okay, so it's not dissimilar from the binomial distribution. It has the same sort of structure but with slightly different coefficients. Now we'll go on to type 2. So this approach models the number of trials, actually should have an S there, denoted N, in a sequence of identically distributed trials before a specified non-random number of successes, denoted R, occurs. Okay, this sounds more like it. It's explicitly we're told N is equal to 5. Okay, that's what we're explicitly told in the question. Now you can rephrase the question. Okay, that's the number of trials that have to be examined. So 5 trials. You can rephrase the question to actually just look at it the other way, the type 1 format, but we'll just sort of stick with this one. Okay, just because we clearly have N equal to 5 and R is equal to 2. So that's the probability mass function there as well. Okay, and again, it's the same sort of construction. Just as a remark, the numbers are slightly different when compared to the previous type 2 case. Okay, so don't get them mixed up. Just think explicitly in terms of K and, or N and R in this instance. Okay, so the mean here is R over P, okay, and the variance there is R times 1 minus P over P squared, okay. So for this case, what we're going to say here, we're going to go with type 2, okay. And what we're going to sort of say here is N is equal to 5, P is equal to 0.2, R is equal to 5, let's write that down there, and that's pretty much everything we need. So we'll go with the type 2 formulation here. N minus 1, the choose operator of N minus 1, choose R minus 1, okay. 5 minus 1, choose 2 minus 1 is 4, choose 1, which is 4. 1 minus P to the power of N minus R times P to the power of R, which is 1 minus 0.2 to the power of 5 minus 2, which is 0.83. P to the power of R is 0.2 to the squared, okay. So working that out, you should get an answer of 0.0819, okay, just around 8.2%. The expected number is the mean of the negative binomial distribution for type 2, okay, and so that's R divided by P, that's 2 divided by 0.2, which gives us 10. So essentially what we should do is, if we're looking for 2 successes, we should expect to be looking for looking through 10 policies. Okay, we'll leave it there. That's grand. So that's the negative binomial, okay. What I might do is in another video actually just looking from the point of view of type 1.